Welcome to this video on the ANOVA test. Let's begin. After watching this video, you should be able to state the steps of an ANOVA hypothesis test and also complete all the steps of an ANOVA hypothesis test. So a quick disclaimer. This video does not provide instructions for any specific technology. If you want to learn how to use a specific statistical software package, you will need to watch a different video. And really simply, the reason I do this is every few years we change textbooks and software, and so I want to have videos that I can continue using year after year, regardless of what statistical software package is being employed. So let's begin. ANOVA. Remember, ANOVA stands for Analysis of Variance. I've created 3 different videos to introduce you to the concept, so this video is just going to focus on the process. So recall that ANOVA is, by definition, a hypothesis test, and so let's review the steps of hypothesis testing. So the first thing is we always have to check that all of our requirements have been met. Then we can write our null and alternative hypotheses. Then we can actually conduct the hypothesis test, and we have 2 methods available to us. We can either use the critical value method or the p-value method. And then after that, it should become very clear whether we should reject or retain the null. So we make that decision based on the results of our test, and then we write a statement to summarize our findings. So here's our example. A teacher wants to compare the effectiveness of 3 different study methods on student performance. So one group studies for the exams just using flashcards, another group studies just by reading their notes, and a third group studies by watching videos. So each group consists of 5 students, and here are their test scores. Now you don't have to, do anything with these, because what we would do is put them into a statistical software package and ask that software to generate either a test statistic or a p-value for us. So we're going to assume that the populations from which this data was drawn are normally distributed, because that's one of our requirements, and if we don't assume that, then we can't do ANOVA. So we're going to make that assumption, and we're going to conduct a test to determine if there is any difference among the scores for the 3 types of study methods at the 5% significance level. So remember, the requirements of one-way ANOVA, and again, I believe I covered this in a previous video, but let's go over them. The first requirement is that my response variable is quantitative. The explanatory variable is usually categorical, or even if it's quantitative, we treat it as categorical. So let's go back to our data and make sure that the response variable is quantitative. So what is my response variable here? Well, the response variable, as you can see, right, the way I'm measuring the efficacy of the study method is through a quantitative variable, which is the test score. So that requirement has been met. The second requirement that we need to think about is that there are k simple random samples, and we usually require that we have at least 3 simple random samples. Otherwise, there would be simpler methods to use. So let's go back to our data and make sure this requirement has been met. So as you can see here, we clearly have 1, 2, 3 different groups, and so that requirement has been met as well. So what are our other requirements? Well, some other requirements are that all the samples have to be independent of each other, and that the populations in question must be normally distributed. So again, we're going to assume that these samples are independent. It makes sense that each student's grade would be independent of the rest, and also that the populations are normally distributed, and that was stated in the problem statement, that we will make that assumption. So the last requirement is probably the most difficult and laborious to check, and it says that the populations in question have the same variance, sigma squared, or the same standard deviation, sigma. Note the standard deviations don't have to be exactly the same, because that's not really a reasonable expectation to have, but as long as the largest sample standard deviation is no more than twice the smallest sample standard deviation, ANOVA may be used. So one thing that's confusing is we go back and forth between talking about the variance and the standard deviation, so that's a little bit tricky. The next thing is, well, I don't know off the top of my head what the sample standard deviations are for the 3 groups. So unfortunately, I'm going to have to go into my statistical software, and I'm going to have to ask it to find those standard deviations. So I went ahead and did that. So the standard deviation of group A, that was the group that used the flashcards, is about 1.9%. Remember, this is a exam grade. For group B, this is the group that used their notes, it was about 1.58. And for group C, this is the group that watched the videos, it was around 3. So remember, our criteria is that we look at the smallest standard deviation. So clearly 1.58 is the smallest among these three. And if we take twice that, we get about 3.16. And so our largest standard deviation, which as you can see here is 3.033, is smaller than 3.16. So this requirement has been met. So now we have our steps, right? So all we've done so far, even though I've been talking for 5 minutes, is we have checked all of our requirements. So now it's time to write our hypothesis statements. So let's go ahead and do that. So recall that in general, for any ANOVA test, the null hypothesis is that all the means are the same, and the alternative hypothesis is always that at least one mean is different. So if we contextualize it in our problem, so remember we have 3 means, we have group A, B, and C. So the null hypothesis is that mu1 equals mu2 equals mu3, or you could say it just in words by saying there's no difference among the average of the 3 test scores. Alternatively, we would claim that at least one set of test scores has a different mean, or is different enough to suggest that it came from a different population. So in any hypothesis test, we can use either the critical value method or the p-value method. Recall that the statistic used in ANOVA test is the F statistic. So let's review that really quickly before we go on to actually conducting our test. So the F distribution looks like this. Unlike the T distribution or the normal distribution, it is skewed. It is not symmetrical. And specifically, it's right skewed because it has a long right tail. And again, this is the most commonly used distribution in ANOVA, or analysis of variance. So remember, when we're doing ANOVA, we exclusively conduct right tail tests, meaning the critical value will be on the right-hand side of this curve. So also recall that the shape of the F distribution will change depending on the degrees of freedom, which are calculated by 2 different things. One is the numerator degrees of freedom is what's called m minus 1, so it's the number of groups being compared minus 1. So in our case, we have an A, a B, and a C group, right? So we have 3 groups minus 1, so our numerator degree of freedom would be 2. And then the denominator degree of freedom is the number of observations. So we have 5 observations minus 3 groups. So 5 minus 3 would be 2. The other thing to remember is the way the F statistic is calculated is that it's the ratio of the between groups variance to the within groups variance. So again, you can use the critical value method or the p-value method, and generally speaking, you would just pick one or the other. You don't need to do both. That would be sort of like vacuuming your kitchen floor and then sweeping it, right? It was already clean after you did it the first time. You probably don't need to do it again unless it was super dirty, right? So you just pick one or the other, but again, for the purposes of this instructional video, I will be showing you both methods, but if you're only interested in one or the other, you can feel free to skip around as needed. Okay, so I'm going to start with the critical value method. And again, I have this computation up here just to remind you what the F statistic is measuring. So if I want to use the critical value method, I have to find a critical value. And this critical value comes from the fact that I'm asked to use a 5% significance level. So we have to use an F calculator in our software, which again, I'm not teaching you how to use the software in this video. I'm just telling you that's what you would have to do to find the critical value. So remember, I talked about my degrees of freedom, right? So first we have to calculate the numerator degrees of freedom, which was the number of groups minus 1. And then we have to calculate the denominator degrees of freedom, which is the sample size minus the number of groups. So the number of groups. So we have to figure out what is the number of groups, how many groups are we comparing, and what is the sample size. So let's go back to our data set, right? So we have 1, 2, 3 groups that we're comparing, and we have 1, 2, 3, 4, 5 samples. So we have 3 groups and a sample size of 5. So that means that I have 3 groups. So 3 minus 1 is 2. So the numerator degrees of freedom is 2. In the denominator, we have the sample size, which we said is 5, right? We have 5 data points for each group, minus the number of groups, which is 3. So 5 minus 3 is 2. So I have used this F calculator, as you can see here. I entered in the degrees of freedom for both the numerator and the denominator. I deleted this value and I just typed in 0.05. And again, I used the greater than or equal to inequality because remember, this is always a right-tailed test. And I'm not sure if you can see it here, but there is a small red line here. So basically the critical value here, as you can see from this number right here, is 19. So what we're saying is that the critical region is anything to the right of that value. And that's because, again, ANOVA is always a right-tailed test. So the critical region is always going to be to the right of the critical value. So anything to the right of f equals 19 is going to lead us to reject the null. Because remember, if this f statistic lands inside the critical region, we reject the null. Conversely, if it lands outside of the critical region, we will retain the null. So at this point, all that's left to do is to use technology to find our test statistic. And I did that. It's kind of anticlimactic, but bam, there it is. Magic happened, and we have an F value of 52.3766. So if we plotted that on our nice little distribution here, you can see it clearly lands well inside of our critical region, and that leads us to reject the null hypothesis. So again, normally at this point, we would just write our problem statement and be done, but since this is an instructional video, I'm also going to show you the same exact problem using the p-value method. So we have to use technology to generate the p-value, and again, kind of anticlimactic, but bam, there it is. There's my p-value. One thing to note, at least with this particular statistical software package that I'm using, I think it's a little bit weird. You can see it says PR greater than F. I'm like, what is this, right? So instead of just saying p-value, as is the case in other hypothesis tests, it's basically specifically indicating that it's using an F statistic, just in case you forgot or you didn't know. And the greater than symbol, I believe, is also meant to denote the fact that this is going to be a right-tailed test. So this is just letting the user know, hey, I did an ANOVA test using the F distribution and using a right-tailed test on the F distribution. So that's what all that silly notation means. Okay, so now we're going to compare that number to the significance level provided in the problem, which is, of course, 0.05. So as you can see, our p-value, I've listed it in 3 different ways. One is this weird thing, right, with the e to the negative 0.6. What is that? Well, this is actually what's called scientific notation, and I have a whole video on it, and I'll link that video in the description if you're really curious. But all you really need to know is that when you have a negative exponent like this, it's going to be a really small value. And as you can see, I can rewrite it as 1.17889 times 10 to the negative 6. And if I write that in standard notation, it's 0.5 zeros and then 117889. So hopefully we can all agree that at least one of these formats, at least in standard notation, this is very clearly much smaller than 0.05. So we conclude that since the p-value is less than alpha, in this case much less than alpha, we would have to reject the null. And of course, this is the exact same decision that we would have come to, or that we came to using the critical value method. So in conclusion, we checked that all of our requirements were met before we started this test. Then we wrote our hypothesis statements. Then we conducted the hypothesis test using actually both the critical value method and the p-value method. And both of those led us to make that decision to reject the null. So let's go ahead and write a statement to summarize the findings that resulted from both the p-value method and the critical value method to reject the null. So at this point, we've gotten so bogged down in the minutia of conducting the test that we might have absolutely forgotten what we're doing anyways. So let's just remind ourselves what this is all about. So what it is about is this teacher had students, she randomly assigned students to 3 groups and asked them to use these 3 different methods when they studied, and then she recorded their exam scores. So our conclusion, right, is to, again, our decision is to reject the null. So we would summarize our findings by saying that there is sufficient evidence to support the claim that at least one test average is different at the 5% significance level. So I want you to pause for a second and reflect on what I just said and think about what that means for this teacher who implemented these different studying strategies. So you might quickly come to the realization that this test is very limiting. So in other words, if this teacher wants to know, okay, great, they're different, they're not all the same, which studying method was best, guess what? ANOVA's not going to tell you. It doesn't tell you which sample or samples differ from the others, and it doesn't tell you how the samples differ. It doesn't tell you which one is better or which one is worse. So again, we have three groups. We have the flashcards, the reading notes, and the watching videos. We know that one of them is not like the others, but we have no way of knowing at this point which one is which. So I'm going to leave you with this question. If you were the instructor, what should they do now? What would you do now to determine which of these three study methods is the best?